Hello, we're going to take a look at the different types of shapes that you need to know in chemistry and some examples of what those would look like. So you're going to fill this in on your molecular shapes note sheet. So first of all, we have the number of regions around a central atom and bonding regions. So you have two columns. So in those first three rows, you should put a 2, 3, 3, 2, 3, 2 for those columns. Names of the shapes: linear, trigonoplanar, and then bent. Those angles, the angle that is getting those electrons as far away from each other as possible is 180 in this situation. Here, the biggest angle possible between the electrons is 120 degrees. And here we're going to have a lone pair. So that is going to take up a little bit more space. So it makes this be a little bit less than 120 degrees because of that. Some examples, carbon dioxide is kind of your most common example of the first one. So we're looking at the central atom only. So here's a Lewis structure. By looking at the central atom only, there's two regions. Even though there's a double bond, this just counts as a region of electrons. The region of electrons, those two will repel each other as much as possible and becomes linear because of that. Next one, best example, I'm going to use lines for my bonds on this, just to make it a little quicker. This is BH3. This is supposed to be an H. There's only three pairs of atoms around, or electrons around a boron. That makes those be 120 degrees away from each other. And then here, I'm going to draw it like we do it a Lewis structure, and that would be sulfur dioxide. In reality, it would. This is how we do the Lewis structure. So two-dimensionally, it doesn't look like it's bent, but this is a pair of electrons, pair of electrons, pair of electrons, and three-dimensionally, it would look more like this, with this being a sulfur oxygen. Oxygen, this is a double bond, but there's three pairs of electrons or regions of electrons, but only two of them are bonding. So that's what's meant by two bonding. Three regions, two of them are bonding. But that lone pair still pushes the other electrons away, so that's why it is bent, because that lone pair is still involved. So here are the next three, and I know you need to flip the page to be able to fill these all in there, but here are the next three. We have four regions on all four of them, all four regions of electrons around the central atom. First case, there's four that are bonding out of those four. Next case, three are bonding, and then next case, two of them are actually bonding. So tetrahedral, trigonal pyramidal, and bent are the shapes for those. And then needs angles. It's not written very well, but it's 109.5. That's the way to get those away from each other as much as possible. Here we have a lone pair. So that lone pair is going to take up more space and push this angle closer together. It's going to be a little bit less than 109.5. You don't need to know the exact number, but it's less than 109.5. And this one's going to have two lone pairs, one here, one back here, which is going to make it, again, less than 109.5. And it's even less than this first one here, but the exact amounts is not that important. So what would be a Lewis structure that would be tetrahedral? Well, as we draw it two-dimensionally on a flat piece of paper, it'd be methane. But if we made these angles, they'd be 90 degrees apart if it was all in one plane. 109.5 is a larger angle by going three-dimensional. Methane is tetrahedral. What about trigonal pyramidal? Well, ammonia is the kind of the most common one out there. It's a lone pair right here. So it'll be trigonal planar. With all the hydrogens on the bottom, kind of making up the legs, if you want to think about it that way, like a tripod, and then nitrogen being this blue atom in the middle. Here this would be the carbon, and the hydrogen's all to the outside. And then bent, again, two-dimensionally on paper, it doesn't look like it's bent, because we're trying to get these, show it be symmetrical. But when there's two lone pairs like this, for water, it is actually bent. So maybe a lot of teachers in the past have written water like this, and you're wondering why. It's because of the bent shape that it has, because these electrons still repel these other bonding electrons, and what the resulting shape is bent. And then the last two is we have 5 bonding regions or 5 regions of electrons around the central atom, 6 around the central atom. We're going to stick with there being no lone pairs. Those of you taking AP chemistry next year, we will add it. What if there's only 4 bonding or 3 bonding or even 2 bonding, and add in lone pairs. But for our purposes of this class, we do not need to do that. So examples would be like, again, on paper, on flat paper, it doesn't look like it's going to make that shape because I'm just trying to make the Lewis structure symmetrical. But three-dimensionally, it would turn into this with P in the middle and all these being H's around it. SF6 is a good example. Sulfur hexafluoride for an octahedral shape. Again, it just looks like a hexagon of some sort on flat paper, but three-dimensionally, it would make this. And by the way, these angles are all 90 degrees for octahedral. And trigonal bipyramidal is the only one that has 2 separate types of angles. 90 there, but then in the middle, it's like a trigonal planar. So those, tough to draw, what I'm trying to do, but these are 120 degrees. So that's the only one with 2 different angles of all the shapes. So those are the shapes that you'll need to know. Again, you're going to look at the central atom to determine how many numbers of electron regions are around it, because those will all repel each other as far away from each other as they can. But if there's lone pairs, that's going to ultimately determine the shape of the actual molecule.